For this next lesson, we're going to start taking a look at the equations of linear relations. So there's three main equations that we're going to use to represent linear relations. The most common one is this form, y is equal to mx plus b, which we refer to as the slope-intercept form. So in this unit, we express the equation of linear relations in three different forms: slope-intercept, point-slope, and general form. We relate linear relations expressed in these forms to their graphs. We also determine the linear relation given a graph, a point, and the slope, 2 points and a point, and the equation of parallel and perpendicular lines. So the first thing is we need to be able to identify what linear relations are based on the form of the equations and what makes it stand out as linear or nonlinear. So the first one, if I put into my graphing calculator and I have y is equal to 3x plus 1, it's going to look like this. If I have negative 2x plus 3, you should get something that looks like this. If I put negative x to the power of 3 plus 1, this is going to be the first one that looks a little different. It's going to look almost like a weird little S shape. If I have x squared minus 3, it's going to look something like that. If I said that I have 1 over x, this one actually looks like it's split into two different equations. If I have 1/2 of x minus 2, should look something like that. 4x is going to look something like this. And 2 to the power of x is going to look something like this. If I'm listing the equations based on whether they're linear or nonlinear, well, the linear ones are going to be y is equal to 3x plus 1, y is equal to negative 2x plus 3, y is equal to 1 over 2x minus 2, and y is equal to 4x. The nonlinear ones that we can see here are going to be y is equal to negative x to the power of 3 plus 1, y is equal to x squared minus 3, y is equal to 1 over x, or y is equal to 2 to the power of x. If I'm comparing the lists from what I see in the linear and nonlinear, write a rule for the equation which can be used to determine whether the graph is a straight line or not. Well, anytime I have a graph with a straight line, I'm always going to have x to the power of 1. We can see that here I have x to the power of 3 in the first case. I have x to the power of 2 in the second case. 1 over x would be the same as x to the power of negative 1, which doesn't work. And in the last case, I have x is going to be as the exponent. So it's not even the base, it is actually the power in that case. In order for it to be linear, I always have x to the power of 1, or I have a polynomial with a degree of 1. If I'm looking at linear equations, a linear equation in the equation form of y is equal to mx plus b, where m and b can be any real number, the graph of the linear equation is going to be a straight line. So in this case, Janine used a graphing calculator to sketch the graph of the linear equation y is equal to 2 over 3x minus 1, and she did her sketch on the grid on the right here. Use the sketch in points A and B to find the slope and y-intercept of the graph of y is equal to 2 over 3x x minus 1. Well, the slope going from these points is I went right 3. My slope is 2 over 3. My y-intercept is going to be where it crosses the y-axis. My y-intercept occurs at 0 and -1, which means I have a y-intercept of -1. If I'm comparing the values found in A with the coefficient of x and the constant term in this equation, well, my slope is my coefficient of x, and my y-intercept is the constant term. For part C, it says, Janine sketched the graphs of 2 more linear equations. Use the grid to determine the slope and y-intercept of each graph. Well, for the first one, if I'm looking at this line, which is going to be the 2x plus 1, then here, if I go from the point down here to the point up at the top here, I went up 1, 2, 3, 4, 5, 6, 7, 8, and right 1, 2, 3, 4. I have a slope of 8 over 4, which can get reduced down to 2. And for this one, my y-intercept occurs right here, where the y value is 1. For the second one, my equation here, then I can see that I have, going from this point to this point, a slope of, I went down 5 and right 2. And I have a y-intercept here at this point of -3. So if I'm making a official conjecture, then M is my slope, which I already knew from when we were doing the slope equations. And the new one is that lowercase b is my y-intercept. So anytime that I'm using this lowercase b for these functions, it's always referring to my y-intercept. Part 2, Hashib used a graphing calculator to graph the linear equation 2y is equal to 5x plus 8. Use a sketch to determine the slope and y-intercept of this graph. Well, my slope going from this point to this point is I need to go up 1, 2, 3, 4, 5, and right 2. So my slope is equal to 5 over 2. And my y-intercept, which we're now referring to as lowercase b, is going to be at the point of 4. Why in this case is the slope not 5 and the y-intercept not 8? Well, that's easy because the y has a coefficient of 2. That needs to be divided from both sides. So in order for this to work, y has to be by itself in the equation. If I divided that 2 from both sides, then I'm going to wind up with y is equal to 5 over 2x plus 4, and that does match the information that we have. So for a slope y-intercept form in the equation of the line y is equal to mx plus b, the graph of an equation in the form y is equal to mx plus b, or a function f of x, which we know can just replace y, is equal to mx plus b, is a straight line with a slope m and y-intercept at b. The equation is known as slope-intercept form, and the graph of an equation in this form can be drawn without making a table of values. So first, determine the slope and y-intercept of each of the linear equations listed below. Well, there's my slope, and there's my y-intercept. In this case, I can see that the equation is out of order, so I'm going to say y is equal to negative 2 over 3 x plus 7. And there's my slope, and there's my y-intercept. In the last case, I see I have a coefficient of y that I need to divide out, so I'm going to divide all the parts by 6. I'm going to say y is equal to, well, 8 over 6 can get reduced to 4 over 3, x plus 1 over 6. And once again, there's my slope of 4 over 3 and my y-intercept of 1 over 6. If I am graphing the equation of a line in the form of y is equal to mx plus b, we're going to look at two ways of sketching the values without using a graphing calculator or a table of values. So the first thing I can do is I can state the slope and y-intercept. Well, my slope is 2, and my y-intercept is negative 5. Mark the y-intercept on the grid, so on the y-axis at negative 5, and use the slope formula, rise over run, to mark 3 other points. Well, if the slope is 2, that's the same as 2 over 1, which means that from that point, I'm going to go up 2, right 1, and there's another point. Up 2, right 1, there's another point. Up 2, right 1, and there's another point. And I can just keep extending this line out, going on forever and ever, using this same pattern. In either direction. I can verify this using a graphing calculator, and this works. The other way that I can do this is I can state the y-intercept. Well, the y-intercept in this case is going to be negative 6. I can determine the x-intercept algebraically. Well, the x-intercept is just when y is equal to 0, just like the y-intercept is when x is equal to 0. So I'm going to solve this, and I'm going to say that 0 is equal to 2 over 3x minus 6. I'm going to add 6 to both sides and say 6 is equal to 2 over 3x, multiply by 3, and 18 is equal to 2x, and divide by 2, and 9 is equal to x. And there's my x-intercept. I'm going to mark the 2 points on the grid. So I have my y-intercept at negative 6. I have my x-intercept at positive 9. And then all I'm going to do is I'm going to connect those 2 points. So I'm going to try and keep it as straight as possible. And then just connect between them. And draw the arrows to use that in extending it. And check to make sure that it works. And in this case, yes, it does.